Here's where we ended last time we met. Line angle formulas. Line angle formulas are sometimes called skeletal structure or stick figures. Bonds are represented by lines, and carbons are present where a line begins or ends and where two lines meet. Hydrogens attached to a carbon are not shown. Hydrogen, oxygen, and halides must be shown. So here I see a Lewis structure, and it's 1, 2, 3, 4, 5 carbons long. So here is a 1 carbon, 2 carbon, 3 carbons, 4 carbons, 5 carbons. That represents this chain. Here at the end, there's a carbon, and there's the bond in the next carbon, so there must be 3 other bonds, and that's bonded to hydrogens, those 3 hydrogens there. Moving up here, there's a carbon at the angle where these 2 lines meet. We see the 2 bonds go into the carbon. Carbon must have 4, so there's 2 hydrogens. And on to the next carbons, the same, 2 hydrogens. We get to this special carbon here called carbonyl carbon, and it's double bonded to an oxygen. Oxygen's happy. It's got its 2 bonds, and this carbon has 1, 2, 3, 4 bonds. End of this line, there's a carbon, and for carbon to have 4 bonds, there's 3 hydrogens, as we see right here. So here's an exercise for us today. Turn the following line angle formulas into Lewis structures. I'm going to have you do one more thing, and that's write a molecular formula after we're done. So there's my line angle formula. So I'm going to go 1, 2, 3, 4. There's 4 carbons. I'm going to make a 4 carbon chain. Between this carbon and that carbon, there's a double bond. Put the double bond in there. So this carbon, I see 2 bonds. It needs 4. So I fill in what it needs with hydrogen. This carbon right here is this one. Presently, it looks like it has 3 bonds. So that makes it have 4. And 4. Now this thing has 4. And the carbon on the end is going to have 3 bonds. So here's the line angle formula, and here's the Lewis structure. So we want to come up with the molecular formula. That'll be C4, H, count them all up, 3, 5, 6, 7, 8. That might be interesting here in a second. Alright, the next thing we have is this thing here. So I see 1, 2, 3, 4, 5, 6 carbons connected in a ring. So far so good. And I see a double bond there, double bond there. Presently, each carbon has 3 bonds, and so when we put in the hydrogens, that's going to give every carbon 4 bonds. And now we have successfully turned the line angle formula into a Lewis structure. So I see 6 carbons and 6 hydrogens. I think there's one more example. Turn the following line angle formulas into Lewis structures. The carbon atom. So there's the backbone of this structure. Now I need to make sure every carbon has 4 bonds by filling in all the hydrogens. And let's go ahead and write the molecular formula. I see 4 carbons and 8 hydrogens. 1, 2, 3, 4, 5, 6 carbons. So for the Lewis structure, I'm going to put out my 6. There we go. 1, 2, 3, 4, 5, 6. 1, 2, 3. Third carbon in. 1, 2, 3. I have a double bond going to an oxygen. So now I'm going to make sure every carbon has 4 bonds by putting in the appropriate number of hydrogen. Don't want to put anything there and give carbon 5 bonds. And there we go. We've turned this line angle into a Lewis structure. And I see 6 carbons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And oxygen. Last topic in chapter 1 is going to be isomerism. What is isomerism? We have lots of different types of isomers in organic chemistry. Molecules that have the same molecular formula but differ in the arrangements of their atoms are called isomers. First flavor of isomer we're going to look at is called the constitutional isomer. A constitutional isomer has the same chemical formula. That's why we wrote molecular formulas earlier. But the atoms are connected in a different order. So you've heard of the pentagon or pentagram. When you hear pent, you want to think 5. That's why we call this thing here pentane. It has a 5 carbon chain. The ane part tells us sigma bonds everywhere, no double bonds. If there was a double bond somewhere, there'd be an E here and there'd be an ene. So there's only 4 different ways you can connect 5 carbons. You can put them all in a chain. You can take one end off and connect it here. Then you could take another one of those off and connect it there. And so here is the 5 arrangements that one can have for a 5 carbon chain that we say is fully saturated. It has all the hydrogens it can have on it. Stereoisomers are compounds with atoms bonded in the same order, but their atoms have different orientations in space. So we already looked at a C4H8 compound. So here is 1 butene, 4 carbon chain. We got the double bond. That's why this ends in ene. These all are going to end in ene. When you see but, you want to think 4. But stands for 4. So since the double bond cannot rotate, we can have this orientation where the methyl groups are on the same side of the double bond, and we call that cis. So we call this cis-but-2-ene. And here is a trans-but-2-ene. I'm kind of old, and we used to just call these things 2-butene, cis and trans, and this would be 1-butene. Then we only stuck in the number hyphenated in here if we had other things out in front that would preclude us from doing that. So notice these are constitutional isomers because they both have the formula C4H8. Same molecular formula, but different order of connection. Well, that's all of chapter 1. Let's go on to chapter 2. So we start out with this thing. And then I put the double bond in the middle of that one. So C4H8 has these 4 isomers. Includes chapter 1. And we'll talk a lot about isomers, constitutional isomers. First up, an acid-base review. The Arrhenius definition of an acid is a substance that you put in water and it gives you hydronium ions. So sulfuric acid here, put that in water, proton comes off that, sticks on water, and you get the hydronium ion. Here's hydrogen sulfate. So I could say acid, base, conjugate base, all that good stuff. So your Chem 1 and 2 book tells you that the strongest acid you can have in water is the hydronium ion. And so sulfuric is a stronger acid than hydronium. It gives its proton to water and you get the hydronium ion. And that's called the leveling effect of the solvent. So for a given solvent, that's going to affect how strong an acid you can have. So protonated solvent, when the solvent's water, is hydronium ion. And there's no equilibrium arrow here. We say sulfuric is a strong acid because it completely disassociates. So here's our acetic acid, and here's water. And we saw that the pair of electrons here can grab that hydrogen, the sigma bond. Electrons then jump onto oxygen, and we get that charge there. And we said this was stabilized by resonance. So the next definition you learned in Chem 1 was the Bronsted-Lowry, which had more detail to it. Acids are any species that can donate a proton. A Lowry-Bronsted base was something that could accept a proton. And we see the same thing here for sulfuric acid. Donates a proton to water. That means water's the Bronsted base. Here's our conjugate acid-base pair. So here is ammonia. And you see it has a lone pair of electrons which can accept a proton off of water, which gives us hydroxide and the ammonium cation. So this example and this one here are nice because we can review this Chem 2 concept that says acid-base equilibrium favors the formation of the weaker base and the weaker acid. This one up here, we can figure it out, but it's up here. I like to look at this and say this is a weaker base than this base. So it goes this way. But since it's a strong acid, we don't really like to talk about equilibrium. We can come down here and look at equilibrium down here and say here's an acid, here's a base, conjugate acid. And we see the equilibrium arrow here being large. That means it favors this size. But let's apply that equilibrium favors the formation of the weaker base and the weaker acid. So water is definitely a weaker acid than the ammonium cation, and this is definitely a weaker base than hydroxide. Now this one here is kind of interesting. Here's our acetic acid. Here is a thing we're going to call methoxide. In general, I can call it an alkoxide. It has an alky group, an organic chemistry part, and then it has oxygen with one bond and the negative charge. And over here, we see this thing called methanol. It's an alcohol. And so if I look at this, here is a base, and here is a base. Which base is stronger? This is going to be a stronger base because it's less stable than this base. This base is more stable because it can delocalize that charge. You can draw resonance structure of these electrons jumping down and the negative charge coming over here. So this base is more stabilized than this base here. And we could ask ourselves, which is a stronger acid? This one here or this alcohol? And in the future, you'll see that this is a carboxylic acid functional group, which implies it's acidic. That proton can come off. And you probably never heard of an alcohol functioning as an acid till you got to OChem. So what's the difference between Ka and pKa? So I have to remind students, P anything is the negative log of that thing. So like pH is negative log of hydrogen ion concentration. So pKa must be negative log of Ka, and Ka is an equilibrium constant. So here we see a bunch of acids, and here's formic acid, which we just saw on the previous slide. We don't have methanol, but we have ethanol down here, ethyl alcohol, and so it can behave as an acid, but so can formic. And if this behaves as an acid, its conjugate base will be ethoxide. I called the other one methoxide. I said they're both an alkoxide. Those names aren't important now. What's important now is understanding pKa's. The smaller the pKa, the stronger the acid. So HCl. In Chem 1 and Chem 2, we learned we don't assign a Ka because it's a strong acid. What makes it a strong acid? It completely disassociates. Well, science has actually found a way to assign a number. It's kind of weird, 10 to the negative 7. Notice, if you take the negative log of 1 times 10 to the 7, you'll get negative 7. And this entry in this table is kind of interesting to me because I'd say what it is, but my daughter says that's not right to say anymore. It's all messed up. It's mentally handicapped because I see hydronium and water, and I see hydronium and water. Seems crazy, but anyway, there it is. HF, hydrofluoric acid, fluoride ion. Notice HCl is a stronger acid than HF. So in an upcoming slide, there's some review. Looks like we're about out of time. And this idea that the weaker the acid, here's my take-home message, or the thing that gets me real excited. Here is an alkane. In future lectures, I'll say there is no functional group of an alkane. An alkane isn't a functional group. Alkanes are relatively inert. They're unreactive. It's impossible to pull a hydrogen off. Well, no, Kim, we can make an acid out of anything. If I pull a proton off of methane, I'm going to have this thing here. Carbon only has 3 bonds, but it's got this lone pair. This is the strongest base known to mankind. How do I know that? This is the weakest acid known to mankind. So notice it has a large pKa, meaning it's a very weak acid. The larger the pKa, the weaker the acid. All right, that's going to be it for today.